Hi and welcome to this short video abstract where we discuss the paper titled Optimization of Exercise Countermeasures to Spaceflight using Blood Flow Restriction by Luke Hughes, Kyle Hackney and Stephen Patterson. This is a review article published in Aerosp Med Hum Perform journal in 2022. So what is the deconditioning effect of microgravity? Well, the absence of gravity triggers remodeling of the cardiovascular, neuromuscular, musculoskeletal systems. The first challenge from Earth to space involves a shift of blood from the lower extremities, causing central blood volume expansion and increased cardiac preload, stroke volume, and cardiac output. Blood pressure, however, is maintained, but this fluid shift is associated with nausea, headaches, and facial edema. Concurrently, neural and downstream skeletal muscle connections begin to adapt to new sensory stimuli and reduced use. Spatial orientation impairment, increased difficulty comparing the mass of objects, and increased reaction time occur during and post spaceflight. In parallel, reductions in mechanical loading and reduced neuromuscular use shifts protein balance to a negative state. Consequently, muscle fiber size is decreased and muscle fiber composition shifts towards faster chain expression. Type 1 fibers appear to be the most influenced and altered by gravity, with in-flight research demonstrating a shift to type 2X with spaceflight. However, mostly all muscles of the lower extremity atrophy during spaceflight, even with mandated exercise and other countermeasures. Alongside this, bone mineral is released from skeletal stores and is a major concern for astronaut health. During 4 to 6 months on the International Space Station, rates of bone loss are 0.9% per month in the spine and 1.4 to 1.5% per month at the hip. For human spaceflight, the challenge of this deconditioning is human safety and the negative impact of astronaut task performance. Future missions will require landing on unknown surfaces and long-term habituation. Extensive physical work will be performed for survival and mission success, while in a physiologically deconditioned state. Decrements in maximal oxygen consumption, neurological reorganization during task performance, weakened skeletal muscle morphology, and elevated risk of bone injury represent significant factors to be mitigated by the international spaceflight community. So how do we perform exercise in microgravity? Well, the exercise hardware on board the International Space Station allows for both high-intensity resistance and aerobic exercise. Target intensities are 70 to 80% of 1 repetition max and 60 to 90% of VO2 max for aerobic exercise. Astronauts are allocated approximately 2.5 hours per day for exercise and accompanying procedures on a 6 days per week schedule, where each day includes both a resistance and aerobic exercise session, typically 45 minutes in duration each, with minimal breaks in between. Upon returning to Earth after long-duration missions, astronauts undergo a post-flight reconditioning program to return them to their pre-flight physical conditioning and prevent long-term health issues, beginning with treatment of any injuries following by functional, endurance and strength exercises, which are gradually progressed in intensity for several weeks until the astronaut returns to work. Future missions place several technical and physiological constraints on exercise countermeasures. The new generation of spacecraft cannot accommodate the size and weight of current exercise equipment used on the International Space Station. It is anticipated that astronauts will have less available time for exercise and device maintenance and repair. Mars missions are expected to cause greater physiological deconditioning during transit, which requires development of preconditioning exercise programs. These will be implemented towards the end of transit to prepare astronauts for re-exposure to non-terrestrial gravity. Upon arrival, reconditioning programs will be required to address physical health issues and prepare astronauts for work, and training programs will be needed to maintain physical fitness during non-terrestrial habituation, which will be constrained by limited exercise equipment and specialist assistance. So why have we suggested blood flow restriction as a countermeasure? Well, briefly, blood flow restriction training is most commonly combined with low intensity resistance and aerobic exercise, generally 20 to 40% of maximum strength, or 40 to 50% of maximal aerobic capacity. And for a full review, see our other videos and our paper in Frontiers Journal of Physiology from 2019. So how could blood flow restriction exercise help with spaceflight? Well, firstly, it may help reduce fluid shifts associated with microgravity. Fluid redistribution and altered cardiovascular function in microgravity can cause orthostatic intolerance upon return to Earth. The concept of applying restrictive pressure cuffs to the limbs to mitigate these changes has been explored previously. In the 1990s, Russia developed inflatable bracelet cuffs designed for the lower extremity to prevent fluid shifts. These cuffs were able to maintain fluid volume and pre-flight cardiac status in a cosmonaut and alleviate discomfort associated with fluid shift. On the International Space Station, the bracelet cuffs have shown positive effects on cardiac performance and mitigation of post-flight orthostatic intolerance. Secondly, it could help increase muscle mass and strength or offset losses during spaceflight. The available blood flow restriction evidence suggests that most apparent applications is to mitigate muscle atrophy. Low-intensity resistance exercise with blood flow restriction increases muscle hypertrophy at a similar rate as heavy load resistance training at the same frequency. Furthermore, blood flow restriction resistance training can increase muscle protein synthesis and increase satellite cell content, both of which are reduced during spaceflight. Data suggests it is more challenging to return to gravity than to adapt to microgravity, and reapplying mechanical load is the most effective method to restore muscle mass. Blood flow restriction exercise has several implications for both in-flight preconditioning in preparation for landing, and secondly, post-flight reconditioning. The most evident benefit for post-flight reconditioning is the low-intensity nature and potent rehabilitation capacity. Thirdly, blood flow restriction aerobic exercise can increase aerobic capacity, vascular remodeling, and associated mechanisms. A major challenge is to mitigate the decreases in VO2 max that occurs during spaceflight. Combining low-intensity cycling or walking exercise with blood flow restriction improves aerobic capacity compared to equivalent exercise without blood flow restriction. Microgravity is a potent stimulus for vascular remodeling. Spaceflight and bed rest studies report decreased arterial diameter, increased arterial stiffness, increased venous diameter, altered venous compliance, and decreased emptying rates in the lower limbs. Peripheral arterial adaptations to blood flow restriction resistance training include increased conduit artery flow-mediated dilatation and resting in maximal diameters. Increased reactive hyperemic blood flow, vascular conductance, capillary filtration, and number of capillaries per myofiber with blood flow restriction resistance training reflect decreased peripheral resistance of the microvasculature. Finally, microgravity leads to elevated bone resorption and reduced bone formation, causing an imbalance in bone metabolism. Despite utilizing a lower mechanical load, evidence suggests that blood flow restriction exercise may benefit bone. Blood flow restriction exercise acutely decreases blood markers of bone resorption and chronically elevated markers of bone formation compared to equivalent exercise without blood flow restriction. However, due to a lack of data on bone mineral density, it is difficult to draw definite conclusions concerning the effect of blood flow restriction on bone. So we've discussed some of the potential adaptations that blood flow restriction exercise may impact during and post spaceflight. However, blood flow restriction exercise may offer some operational benefits if applied in space. Firstly, it requires minimal equipment and less space and loading capacity than current protocols. This in turn would reduce vibration transmission to the spacecraft and may reduce exercise-specific and overall mission costs. It also offers a more efficient method of training. Due to exercise time and equipment constraints for future missions, combining exercise methods to facilitate rapid adaptations is vital. Efficient training describes the process of reducing training volume while maintaining effectiveness, identified as a strategy for optimizing exercise countermeasures. Blood flow restriction exercise appears to offer similar aerobic benefits with less volume of overall work. Furthermore, aerobic exercise with blood flow restriction increases muscle mass and strength, offering an opportunity for a more efficient method of training during spaceflight and allowing more time for mission-related tasks. The low-intensity nature of blood flow restriction exercise could reduce the incidence of strain-related injuries from in-flight training. And furthermore, blood flow restriction exercise could and would provide a potent rehabilitation tool for any injuries. In conclusion, blood flow restriction could offer several operational and physiological benefits during different phases of spaceflight missions as a standalone and complementary therapy. Substantial terrestrial findings support the efficacy of blood flow restriction training for improving the structure and function of the muscular and cardiovascular systems. Emerging data suggests that blood flow restriction exercise may have beneficial effects on other tissues, such as bone and tendon. However, these effects are largely unknown and require further investigation. At present, there is no rigorous evaluation of blood flow restriction during spaceflight or ground-based analogues. And further research in the use of blood flow restriction as an exercise countermeasure to spaceflight is warranted. For further videos, follow us on social media and our YouTube channel.